Okay, it is 2 a.m. and your phone buzzes. A user says your checkout is broken. It is so slow. So you sit up and you go look at what is happening. And here is the strange part. There is nothing to look at. Think about how would you normally debug this on your own laptop, right? You would drop in a print statement just a line that prints out, hey, I got here, and rerun it. Or you would attach a debugger, that is the tool that pauses your code line by line, so you can poke around and see exactly what it is doing. That is how we all learn to find bugs. But none of that works here, and it is worth being really clear about why. One, this thing is live, it is serving thousands of people right now. So you cannot just pause it to look around, freeze it for 1 second, and you have frozen it for everyone. Two, you cannot print and rerun because it is already running on machines in some data center you will never physically touch. And three, remember this is not one program anymore. That one checkout request hops across a dozen separate services. Checkout, inventory, the database, a cache, payments, each on its own machine. So the request you are chasing is not sitting still in one place for you to inspect. It is scattered across the whole system. So how do you debug something you genuinely cannot see? So you cannot look in, which means you have to flip the whole thing around. Instead of watching the system run, which you cannot, you set it up ahead of time so that the system tells you what it is doing constantly as it runs. Every service as it works emits little signals about what just happened, and those signals flow out to somewhere you can read them. And that practice, making a system explain itself from the outside, has a name. It is called observability. And honestly, that word gets overcomplicated. At high level, observability is not about staring at fancy dashboards. It is just this one idea. A system you cannot see has to tell you what it is doing. And it does that with three kinds of signals. And the cleanest way to hold them in your head is each one answers a different question about our slow checkout. The first, is something wrong at all? The second, where across all these services did it go wrong? And the third, why is it broken? Where and why? So let's take them one at a time and watch them actually find our 2 a.m. bug. Okay, question 1. Is something even wrong? And for that, you use a metric. A metric is just a number measured over time. Requests per second, average response time, the percentage of requests that failed, how full the CPU is. You put these on a chart and you watch the line going along, flat and calm. Flat and calm until one night. It spikes. That is your alarm. That spike at 2 a.m. is literally the thing that woke you up. So, a metric's whole job is to shout, hey, something changed, come look. It is a smoke detector of your system. Now, you could measure 1,000 different numbers and drown. So, here is a genuinely useful shortcut from the folks at Google who run this stuff at massive scale. For any service your users touch, if you watch just 4 numbers, you will catch almost everything. They call them the 4 golden signals. 1. Latency. How long are requests taking? 2. Traffic. How many are coming in? 3. Errors. How many are failing? And 4. Saturation. How full are you? How close to your limit? Latency, traffic, errors, saturation. And notice the first one, latency creeping up, is very often the early warning that you are getting overloaded, which is exactly the can you see your full question we ended up on last time. This is you seeing it. And one important habit here, because beginners get it backwards, do not set your alarm on CPU hit 90% because honestly, high CPU is sometimes totally fine and low CPU does not mean the users are happy. Instead, alarm on what the user actually feels. Checkout is slow, that is latency. Checkout is failing, that is errors, right? Alert on what hurts or not on what is merely busy. But here is the catch with the metrics, and it is the whole reason we are not done. A metric is aggregated. Checkouts P99 latency this minute. The slowest request, remember, was 3 seconds. That is one tiny number, and it is so cheap to store and watch compared to keeping every single request in full detail. But that is the one trade. By squashing every request down to that one number, it throws away all the detail. It cannot tell you which requests those were, or whose, or why. So a metric is the perfect alarm. It tells you fast that something is wrong, but it can never tell you what. For that, you need the second signal. Okay, the alarm told us checkout is slow, 3 whole seconds. But where? Because remember, checkout does not work alone. To serve one order, it calls the inventory service, which calls the database, which checks a cache and it pings payments. So, when the whole thing takes 3 seconds, which of those was it? Go on, take a guess. Inventory, the database, you cannot write, and neither can the metric. It only ever knew the total, and you cannot just guess and restart things either. Not in a system with a dozen moving parts. Guess wrong at 2 a.m., and you have burned an hour poking at the wrong service. So, we need something that can point at the exact spot, and that something is a trace. And this, honestly, for me, this is the one that does the real work here. A trace is the story of one single request's entire journey across every service it touches. Here is how it works. As our one checkout request travels through the system, each service it passes through records a little span, and a span is just a stopwatch. It says, I, the inventory service, worked on this request from here to here. That took me 2.8 seconds. Now, string all the spans for that one request together in order, and you get a picture. It is called a trace waterfall, a stack of bars, one per service, each as wide as the time it took. And the big outer bar is our whole 3-second request. And you read it in one glance. Almost the entire 3 seconds is one long, fat bar sitting inside. Checkout's own work was tiny, the database was quick. But there it is. Checkout waited 2.8 seconds on the inventory. And that is your answer. That is exactly where the 3 seconds went. And that is the clean, purpose built way to get it in a system this spread out. It is the tool made for exactly this job. So, the natural question is, how do all those separate services on separate machines know they were working on the same request? And this part is really simple. The moment the request first arrives, the system stamps it with a unique trace ID. Think of it like a tracking number on a parcel. Let's say A7F3. And remember request headers from the HTTP video, those little labels that ride along with every request. Well, that ID gets tucked into them and carried to every service checkout calls. So every single service tags its own span with the same ID, A7F3. And then the tracing system just gathers up everything stamped A7F3 and stitches it back into one story. No shared ID, and you would just have a pile of disconnected stopwatches with no way to know which belong together. Oh, and one nice detail. Remember how we sometimes hand work off to a queue for a worker to pick up later? The trace ID writes along in the message as well, as long as you remember to tuck it in there too. It does not cross on its own, so even the work that happens later on another mission stays part of the same request story. The thread never breaks. One last thing quickly. So it is honest. At scale, thousands, even millions of requests a second, you cannot record a full trace for every single one. That would cost a fortune. So you keep a sample. And the smart move is to try to hold on to the interesting ones. The errors, the slow ones, the 2 a.m. ones, and throw away most of the boring, fast, successful traffic. Keep the ones you would actually want to look at. Okay, the trace pointed the finger straight at inventory. So now, the last question, why was inventory so slow? And for the fine detail, the actual specific what happened, you go to the logs. A log is the most familiar signal of the three. It is just a timestamped record of an event, a line the code writes down as it goes. Honestly, it is that humble print statement from the very start of the video, all grown up. So, we open inventory's logs and read its story for our one slower order. 10:42:03 inventory starts reserving stock. Then 10:42:05 waited 2.8 seconds for a database connection, and right there is our why. The database connection pool was exhausted. Okay, what does that actually mean? Picture it like this. Inventory keeps a small set of open connections to the database, let's say 10 of them, and every request has to grab one, use it and hand it back. And right now all 10 are taken. So request number 11, ours, just has to stand there and wait for one to come free. That little set of 10 is the pool, and exhausted simply means everyone was in use. So inventory itself was not broken, and the database itself was not even slow. Our request was just waiting in the line for a connection that never freed up. And everything is already taken. That is exactly the kind of overload we spent last time learning how to see, right? But logs come with their own problem, and it is the mirror image of the metrics problem. A metric threw away too much. Logs keep everything, and a busy system writes millions of lines a minute. So the hard part is never do I have the information? It is can I possibly find it? The one line that matters buried in a flood. So, two habits turn that flood into something usable. The first, write structured logs. Instead of human sentence, which you can really one grep through, you write neat fields. Service inventory, user 42, event pool exhausted. Because once it is fields, you can search and filter it like a database. Show me every pool exhausted from inventory in the last hour. That is the difference between finding it in seconds and never finding it at all. And the second habit, this is the good one. Tag every log line you write while serving a request with the same request ID from the trace, our A7F3. Because once you do that, watch what happens. You can pull up every log line from every service that touched that one user's broken order. Checkouts lines, inventories lines, the databases lines, all of it in order, stitched into a single timeline. The complete story of what happened to that one request across the whole system. So the why usually shows up right here in the logs. Though, fair warning, sometimes it only fully clicks when you read the log next to the trace and the metric. They really do work best together, which is exactly where we are headed. Oh, and one more rule because logs are so detailed and this bites beginners immediately. Never log secrets, no passwords, no auth tokens, no full card numbers, none of it. Because a secret written into a logs is just sitting there in plain text. For anyone who can read the logs, log what happened, charge the card, never the sensitive value itself. So let's tie it together because the real point is not any of these three. It is how they work as a team. Watch our 2 a.m. bug get solved, one signal at a time. The metric goes off, checkout latency just spiked to 3 seconds. And now you know something is wrong. That is the alarm. So you open a slow trace, it waited 2.8 seconds on inventory. And now you know where. That is the map. So you read the inventory logs for that one request, database connection pool exhausted. And now finally you know why. That is the story. Is it broken? Where and why? Alarm. Map, story, metrics, traces, logs. That is the whole loop. And it is the reason you keep all three instead of picking a favorite. And the quiet thread running through the entire thing, tying it together, that one request ID. And one name to just file away. That is all. There is a common open standard for emitting all three called Open Telemetry. You do not need it today. It only means the tools that collect and show all this can speak one shared language. And honestly, this is a big one because it is the eyes behind everything we have built lately. Every trick from these last few videos had a hidden requirement, right? To cache smartly, to rate limit, to shed load, to tip a baker. You first have to be able to see what your system is doing. Well, now you can. So, we have built up a whole toolbox now. Caching, rate limiting, retries, queues, back pressure, breakers, and finally the eyes to watch it all. Next time, we get to do the part that has all been building towards. We take all of it and put it together into one real complete system from the front door to the database. That is where we go next. But for today, remember this. When production breaks and you are staring into the black box, do not guess. Make the system explain itself. Is it broken? Where? And why? See you in the next one.